So tomorrow, the lab kit and book pickup is tomorrow morning from 11 to 4 p.m. Okay, and homework 1 and homework 2 are going to be due 9:27 and 11. I'm not assigning any extra asynchronous work other than what's listed on the homework schedule for today, and these two things on mastering. So I think you have enough to do until Monday to work on, and then the videos, as I told Renato, those are for you to watch and take notes and write down questions that you may have after watching the video. And you can bring up those questions either in class during the break or after class if it's a quick thing, or you can come in 10 minutes before class, and I'm happy to talk with you right before class. So that was one of the questions on the questionnaire. And also, office hours are great. If they're longer questions, probably should save those for office hours. So anything quick you can take care of before class, in between classes, or after class. But if it's a longer type of question, probably should come to office hours to get help on it. Okay, so AP Classroom has the questions for today and the videos for today. I also added textbook reading that you can do instead, if textbook things are you prefer that. Okay, so we have a little opener today. So here's our opener, and we want to figure out how many moles of gold atoms does it take to reach the top of SHS. Okay, so go ahead, write in your notebook, and I'll give you about 5 minutes to work on this. Up here, so the 18 meters, okay, and we want to figure out how many atoms that's going to be. We know that the radius is 144, so the diameter is going to be 288 picometers. So 288 picometers is the diameter of one atom. So if we take this 18 meters and we say one atom, 288 picometers, okay, and then we want to make sure our meters and our cancel out. So we have 1 picometer is 1 times 10 to the minus 15. And if you didn't do it exactly this way, that's okay, as long as you understand. So that cancels out, and that will give me the number of atoms, and then I can change that to atoms by multiplying by, I know that there are, in 1 mole, there are 6.02 times 10 to the 23 atoms. I'm sorry if my handwriting is really bad. It's partly just trying out different platforms, and they all seem to work differently. Okay, so what I got for the moles, I got about 1 times 10 to the minus 10 moles of gold, which is actually not that much, right? Like these atoms are surprisingly small, but to get to the top of the building, it's, so you can see this is not that many moles. And then once I multiply this to get the, I use the atomic mass of gold. So that's 196.97. And I'm not going to use my sig figs for now. I got about 2 times 10 to the minus 8 grams. So not a huge amount to get to the top. And I was actually kind of surprised, because I thought, oh, well, atoms are so small, it should take a lot of them. But I guess in relatively speaking, they're not that small. Okay, let's see. The diameter would be 288. Like if it's like, here's the middle of the circle, and then a radius here and a radius here. These conversions, you should have gotten feedback at this point. And so if there's anything on there that you don't understand, but I was going to go over at least a couple of these. So for some reason, 9 was kind of a stumper. Here we have moles of argon, and you want atoms. So in number 9, It's actually, maybe it was the fact that it was number 9 and you were doing harder ones before. If you have moles of argon and you want to change the atoms, all you have to do is multiply by Avogadro's number. So that's how many atoms are in 1 mole. Okay, so that will give you the answer for number 9. Number 10, okay, so the mass of that many molecules of glucose. So again, here you're going to take 2.34 times 10 to the 24. This is molecules. Okay, so whenever we have to go from particles, small stuff, to mass, we have to go through moles. So again, we're going to use Avogadro's number. But this time that's on the bottom since we need to cancel out the molecules. Okay, and then to get to mass, we need to multiply by the molar mass of glucose, which was about 180. And so take that, divide it by that, multiply by that, and you get the answer. Okay, and then number 11, atoms of oxygen. So I didn't explicitly explain, I mean, we did one of these in class, but I think it's partly just thinking about, you know, how do I translate this molecule and use the ratios that are shown in this molecule? We know that for each molecule of C6H12O6, we have 6 atoms of oxygen. So if we have this many molecules, then we just have to multiply by 6 atoms of O over 1 molecule. Okay, so that will give us the number of atoms of oxygen. So the other thing that you probably never saw, I don't know, until this time, I don't know if, I'm not really sure. If we have 1 mole of C6H12O6, this will give you 6 moles of carbon, right? 6 moles of carbon have to go in here to make up 1 mole of glucose. This also gives you 12 moles of hydrogen, and it also gives you 6 moles of oxygen. So those relationships are built in to the 1 mole of glucose. Just like if you had 1 molecule of glucose, you have 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. All right, is everybody okay with this? Go ahead and ask if you have a question. Okay, you can give a thumbs up if you're all good. All right. Okay, so let's go on. And there are more practice problems right here if you want to do more practice, and I'm happy to provide the answers if you want to try those and do more practice with this. Okay, so we're going to go into mass spectroscopy, and my hope is that we can finish this part by the end of class 1 and then get into naming compounds and writing formulas in class 2. That's my plan for today. We'll see how far we get, but I think we will at least cover the mass spec before the end of the break. So here, hopefully you had a chance to play with Build an Atom and get familiar with these particles again. So we're going to take a look at 2 atoms or ions. Remember, an ion has a positive or negative charge. Okay, that means it does not have the same number of electrons as protons. All right, so go ahead and in the chat, or if you feel brave and you just want to speak up, what is this first atom or ion? So first of all, we want to answer, is this an atom or an ion? And the red is a proton. Okay, the blue are electrons, and I usually call those E minuses, and then the gray are neutrons. Usually, that's not exactly neutrons with a little 0. Okay, so protons are usually P+. Okay, so we have an answer from a couple people. Be. Okay, so Be is beryllium. That is correct. So we have 1, 2, 3, 4 protons. All you have to look at is the protons, and you know what atom this is, okay, or ion. And so if you take a look at the, oh, and we should say this is an atom, right? Because we have 4 electrons, so -4 charge, +4 comes out to 0. That means it is neutral. All right, how about the second one? Is this an atom or an ion? And be specific in your answer, whether it's an atom or an ion. Yeah, it might be a little hard to count these red things. That thing on the bottom is down there. Okay, and be specific about what element it is. Okay. Yep, I'm seeing oxygen. Okay, so we have 8 protons. Okay, so here this is a ion because if you count the electrons, we have 10 electrons. So the overall charge of this is an oxide. So ion. So again, here negative ions have this "ide" ending here. So this is O2 minus, okay, oxide ion. And how many neutrons do we have? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 neutrons. Anybody know what the mass number is? 16. Yes, 16. Okay, so 16 is the mass number. That's equal to 8 protons plus 8 neutrons. The mass of these is about 1. So this is roughly the mass of this oxygen ion, oxide ion. Okay, let's go on to the next thing. Okay, now this is asking, are these 3 things isotopes? I should have probably just written down how many protons, and let's see. Yeah, I picked these. So this is 8 protons, 8 protons, and this is also 8 protons down here. So are these isotopes? Okay, I'm going to call on somebody to explain what they think isotopes are. All right, Braden, you were late, so let's see. Braden, go ahead and do you know what isotopes are? Exactamundo. Okay, so we're going to go through here. We have how many electrons here? We have 10 electrons. So they don't necessarily have to be atoms to be isotopes. These all, actually, I may have miscounted here. Let's see. This one has 8 electrons, right? That one has 8. I can't see that one on the side. Okay, yeah, this also has 8. So even though this first one has 10 electrons, this is still an isotope with these. These are atoms, oxygen atoms. This first ion, this oxide ion, has 8 neutrons. And as Braden said, we have different numbers of neutrons. Here we have 9 neutrons, and we should have 10 here because this is oxygen 18. Okay, so we have these 3 different isotopes. So this is oxygen 16, the most common type. This is oxygen 17. I should write out the name, but I'm being lazy here. Okay, so technically I should write this out. Another way to express this is like this. 18 at the upper part here. Okay, and then down here is the atomic number, which would be 8. All right, so those are isotopes. Now, if you take a look at your periodic table, what is the atomic mass? I saw that somebody put the atomic mass in there. So on the periodic table, this one says 16. Others say 15.9994. If we have these other isotopes of oxygen, why is it that our mass is reported as 16 on the periodic table? Well, we're going to find out right now. So it turns out that each sample of oxygen has an isotopic abundance, an isotopic percentages in each. Okay, can you guys hear me? It's saying my internet connection is unstable. I hope so. Okay, so if you take oxygen from one part of the Earth and then compare it to oxygen that you find in outer space, the isotopic abundances are different. Now, this is a pretty new idea, though they've known about it for quite a while, but they can now use isotopic abundance to figure out where a certain rock in the world came from. So if you find, for example, tin in Argentina, and then you find tin in Asia, those samples of tin may have different isotopic abundance, and we're going to talk about what that means. So here, this is what is actually reported on the periodic table, the average atomic mass. Okay, it's not of a particular isotope. It's a weighted average. And you guys know all about weighted averages because you're always using them in school. So here we have the grades of Jimmy. Okay, Jimmy's got, his teacher has set up these weights. These are the scores that Jimmy got. No, I should say not yours, but Jimmy's. Okay, so looking at this, wow, he's got a great homework average. What's his grade actually closer to? And don't calculate it. Go ahead, somebody can just unmute and speak up. Yeah, sure. And the reason why you're saying that is because the weight of the tests is much more than the labs and the homework, right? So Jim's average grade is actually is probably closer to 80 than to 100, right? Because homework is only 10%. Well, this is exactly the same idea that we use for average atomic mass. So here, I'm going to do the couple examples for you, and then you guys are going to work on some different problems with this. But here, we're going to calculate the average atomic mass of schmidium. Full disclosure, schmidium is not a real element. Okay, so if the actual masses are not given, we are going to use the mass number as the mass. So to calculate the average atomic mass, what we're going to do, and I'm going to show you we're going to take the mass here, so you guys see that here, that comes from that, take it times the abundance, and we have to change the percentages to decimal places. And then we take the next one, take it times the decimal. Then we take the next one, take it times the decimal. And then we add those together. Basically, we're weighting each mass by its abundance. And so the actual atomic mass of schmidium is 301.1 AMU. Now, AMU is exactly the same number as grams per mole, but we're talking about the mass of one, well, in this case, an average schmidium atom, okay? Okay, any questions with this? Let's try this one. Okay, this one says, calculate the percent abundance found in nature of chlorine. There are only 2 naturally occurring isotopes. Okay, and it's telling you that you need to go to the periodic table. So if I go to the periodic table, by the way, this one is posted on Google Classroom now. Chlorine, if you look, is 35.45 AMU. Okay. And it says report to nearest tenths place. Okay, so how are you going to do this? Well, in this case, we've got the average atomic mass and we have the masses of these, but we have no abundances. Okay, if you want to give it a try, I'll give you a minute to think about it first. Okay, so I'm going to say that X is the abundance of 35 chlorine, and Y is the abundance of 37 chlorine. And those abundances have to add up to 1. Okay? So then I know that the mass of 35 chlorine is 35 AMU. Okay, and then times, I'm going to take that times X. That's my abundance, so that looks terrible. Let me use a dot instead. And then I have my 37 AMU times Y has to equal 35.45 AMU. Okay, so now we have two equations, two unknowns. I can substitute in for, I don't know, we can, it says the percent abundances, I can use either one. So I'll just say X equals 1 minus Y, and I can substitute in here for X, okay? And I can solve for Y, and then I'll get my abundances. So if we take a look here, this is what you should get. Okay, so 25%, this is equal to Y, and this is equal to X. All right, so now we're ready to look at the actual, how this relates to mass spectroscopy. Now you're gonna see a crazy looking instrument. These are really cool instruments, and they use really, it's actually, you know, an electric field and a magnetic field. And you do not need to be able to explain this instrument. Okay, this is just kind of like, if you're more curious about how it works, this is the actual instrument. Basically, think about if you saw a very, very heavy ball bearing, a huge metal rolling sphere going down Highland Ave, and then you saw a tiny little metal sphere going down Highland Ave. Which one of these would be able to be moved like out of its path better? A large, huge thing or a tiny thing? Well, it's much harder to move a large, hard thing into a different path. And that's basically what the mass spectrometer does. It separates out the lightest and the heaviest things just due to their mass, how they interact with this magnetic field. So they have to ionize the sample in order for them to interact with the field. So anyway, I'm going to let you guys look at that. And if you want to learn more, feel free to ask questions. The thing that you need to know how to interpret is this. Okay, so what the mass spec does is basically counts the isotopes that come out. So you can see here, right, there's very little 78, there's a little more 80, and these kind of got moved over. I'm not sure why. 82, 83. What's the mass closest to, the average atomic mass closest to? So let's take a look at a couple of these questions. All right, so here, chlorine has 2 isotopes. How many molar masses are possible for a Cl2 molecule? And this is not a good one to start with. Let me see. I'm gonna skip ahead to this one first. There we go. This is a more fair one. Okay, so read the question and send me a private chat. Tell me what you think the answer is. So there are 5 of the 5 of the isotopes. Okay, so technology. Okay, so the answer was 3. There are 5 naturally occurring isotopes. So oxidation states has nothing to do with mass spectroscopy. The second statement, right? If you have 35 neutrons, that would give you 65 for the mass, and there is no 65 here. And most common isotope is 65 zinc. Well, there is no 65 zinc again. And again, here, the last one, the charge has nothing to do with the mass spec. All right, I will try not to make a snafu with this one. This is a little harder to think about. So think about how many different Cl2 molecules we can have if we have two different isotopes of Cl. All right, so the answer is 3. Okay, so yeah, if we have, this is basically, if we're looking at the chlorine atom, we have a 35 chlorine. The combinations that we can put together would be these 3 combinations. Just imagine that they're different isotope atoms. So that's why 3 is the correct answer. The charge comes in at the very beginning. So in order to actually accelerate the ions through an electric field, they have to have a charge. So you basically, I'm not sure exactly, it might be a plasma that rips off some electrons, and you basically make them all positively charged. So they come off as ions. Most of them end up just losing a single electron, but some of them could end up losing more electrons. So they have to kind of adjust for that fact. So, right, things that are charged more will, react differently with the electric field. So basically, it's probably easiest to think of it as all of them having just a positive charge, and they go through, and then the mass to charge ratio is just adjusting for the fact that if you have a +2 charge. But I wouldn't worry about that. Just assume that they're all positively charged. It'll probably help you think about it more easily if you just think. Yeah, so that's why you have to kind of account for the charge that way. Okay, let's come back together. All right, I'm gonna share my screen with the questions, and I'm gonna ask 2 people to pick a question to go over, probably the multiple choice, just because those will be quicker to share. Where are we? Okay, here we go. Okay, let's see, Renato, could you pick one of the questions and explain to us what you decided, what was the answer? Are you there, Renato?
Oh, is there a way that I can ask a question that I had no clue on how to do it?
Okay, yeah, sure. Which one?
I was confused about.
Well, I mean, so we could have just like looked it up on the periodic table, right? So that's our, basically we're going to use just, oh, sorry, something's, we're going to use this number kind of to do a check, but these we're all going to multiply by the abundances. Okay, so multiply, but we have to first change these into decimals. Okay, so again, here we're going to multiply, but change these to decimals first. And then we're going to add them all up. And then we should get this answer. If you get an answer that's really different from 65.38, then you know that you did this incorrectly. So, and it says to round to the nearest tenths place. So you should get something very close to 65.4 grams per mole, or AMU. I guess we should use AMU since we're looking at atomic mass here, or doesn't matter, either one. Does that? Well, let's see. Luis, would you like to pick one to go over? Luis, are you there? Uh-oh. At the average, for bromine, it's 79.9 AMU. Let me just make sure. Yeah. So most people probably are going between these two, and selenium is 78.97. So if you take a look here, something with bromine has to be really close. You see how 79.9 is really close to 80? So we would have to have mostly 80, almost all 80 for it to be bromine. So so this question, like, you can try to estimate, but you might not get exactly the correct, right, the correct relative abundances. So this is a question of like, okay, if I have bromine and its average is 79.9, so you kind of have to think, oh, it must be weighted very heavily towards 80. So for bromine, we would expect something like much higher than 50%. So that's why bromine's not the answer. Now, selenium is also in that range, and then the rest of them are really not very close in terms of, right? Because if you look at this, you know it's somewhere in between 78 and 80. So, yeah, so that's why selenium is the answer. So this is the correct answer right here. But this is a very tricky problem. You probably picked like the hardest multiple choice problem of the 5. Okay, any questions? Yeah, so this will only work when you have 2 isotopes, right? Because otherwise we'd have another unknown. But here I just assigned some variable to one of the isotopic abundances, one of the relative abundances, and then the other variable to the other abundance, and I say that they have to add up to 1. And then I set up my other equation, my average atomic, my weighted average equation over here, and then I substitute in for one of the variables and solve for the other. Okay, so I'm going to call on somebody in a minute. Okay, so and let me give you the formula of zinc nitrate. Here we go. And don't use your calculator, okay? Just estimate in your head what the answer is. Okay, so we want to know how many grams of zinc nitrate contain 48 grams of oxygen atoms. So I'm going to start you off by, I make sure I would start off by changing this to moles. Okay, so 1 mole oxygen. I'm going to give you a head start here, 16 grams. Okay, because we have atoms here. So, and then we got to connect to this. Okay. So we need to change to moles of zinc nitrate. And I'm missing a. Okay, moles of oxygen atoms. So we need some numbers here. And then you need to change this to grams. Okay. Okay, so I'll give you a minute. Okay, get out your periodic table, find your molar masses, and then do this mental math in your head and see what answer you get. Okay, everybody have an answer in their head? Okay, we're going to go on to the answer. Okay, so the answer is 1. Okay, so here's the setup right here. So you kind of have to do an estimate and estimate the answer using your mental math skills. The reason why we're going to be practicing this because on the multiple choice part of the AP Chem exam, there is no calculator. So no calculator is allowed during that part. So we'll continue to do some of these mental math problems as we go along. Okay. So the answer is number 1. You can make a note of that and then probably go back to it. Okay, so we're going to shift gears now and go to a little bit of bonding and compounds. So would somebody like to explain what a compound is? Let's see, who can we call on? Luis, are you there now? You with us? Much it. So we have 2 different types of atoms, or it could be 3 or 4, but we have different types of atoms in there. All right, so for ionic compounds, remember we're going to have metal and nonmetal. usually. And we could have polyatomic ions. Okay, so the smallest units are formula units. Basically, what the formula is showing is our smallest unit. And they make crystal lattices. Through ionic bonds. So these ionic bonds, remember, are the attraction between positive and negative. So it's basically forces between these ions that are holding the crystal lattice together. And the crystal lattice can be thought of as a very well-ordered, structured crystal. And they have different lattice types, but we're not going to really learn about that in this class. But there's different ways you can stack and pack these atoms together to make different patterns that the lattice makes. So that's our ionic bonding. These are very strong bonds. These are solids, ionic solids, these compounds. Molecular compounds can be solid, liquid, or gas. Okay, they can take on all three states of matter. Just depends on how tightly the molecules are held together. And so with molecules, we have distinct individual molecules. Okay, so I'm drawing some very ugly looking water molecules here. And our smallest unit is a molecule. They're held together with covalent bonds, which is the sharing of electrons. Basically here with a covalent bond, I'm going to draw a very rough covalent bond. If we have our positive nuclei and then we have our electron clouds, that doesn't really look like a cloud, but you can imagine that these electrons are attracted to those nuclei and vice versa. Okay, and so the sharing of electron creates like kind of a density between the nuclei of the atoms, density of electrons, and that holds the atoms together. They're usually brittle. They have pretty low melting points and boiling points, whereas ionic solids have very high MPs and very high BPs. Okay, any questions on that? Just kind of the characteristics of these two types. About, I don't know, things like bread, right, compared to salt. I mean, I guess you've only seen salt as a powder, but salt is really hard. Like if I'll try to get my salt crystal out at some point, but yeah, brittle means that it just breaks easily. They can't deform, but they're relatively strong in terms of like if you want to break them apart, you're going to have to apply more force usually than for covalent compounds. Now, I mean, these are just kind of general characteristics that it doesn't, like for specific compounds, you may have a much stronger covalent compound than a ionic compounds in specific cases, but these are kind of general characteristics. These will break along their lattice planes, but you kind of have to strike them in the right way to get them to break. These will just break anywhere. I don't know, the bonding forces are just usually lower, but it's not always the case. There are exceptions. Okay, so let's go here. So we're going to go through here and we're going to just label through. And I'm just going to go in order of people in the class. Actually, I don't know. Some people are having trouble with their the mute. So, but I don't know, maybe I'll just do a couple on my own first, and then we'll see if you guys can complete. We're going to label these as ionic or molecular. Okay, so this first one, we have metal, non-metal. This is ionic. Okay, second one, this is calcium is a metal. This is a polyatomic ion made of nonmetals. This is ionic. Now, just a reminder, here's the periodic table. Okay, these are all metals here. But then we have boron, silicon, germanium, arsenic, antimony, tellurium. These are our metalloids. Then we have nonmetals, and hydrogen over here is a nonmetal. Okay, the rest are metals. Okay, next one. These two things are nonmetals. This is a molecular compound. Ti, sulfate. This is ionic. All right. Any questions with this? You're going to be working on these problems in a very short time. So, and that'll give you more time to look at the table and stuff. Okay, everybody okay? Go on for now. All right, so in terms of naming compounds and writing formulas, for these binary molecular compounds, this is where we have just two nonmetals. All right, all we're going to do is use these prefixes to name. And there's a couple of like kind of rule things, but not, I mean, they're not too many rules. So let's do a couple examples here. So for SO2 right here, okay, SO2, we look at the first thing here. This is sulfur. And we just use the element name, okay? So for the first element, sulfur. And for the first element, if there's just one, you don't use mono for the first element, okay? You just use the element name. But if it's more than one, you can use a prefix in front, like the next one right here. So this is sulfur, and there's two, so we're going to use the prefix di. So this is sulfur dioxide. Okay, so sulfur dioxide. They use that as a preservative. The next one, diphosphorus. So di means two. Phosphorus is our phosphorus. So we have P2. Pent means 5. And notice that for the second element, we change the ending to IDE. So this becomes pentoxide. So it's O5. So that's how we name and write formulas for molecular compounds, for these binary moleculars. Now, we're not going to do any organic chemistry. If we have time at the end of the year, we will. But we're just going to learn to name these. Okay, any questions on this? Okay, let's go on to ionic compounds. So this list, several of you have seen this already. I highlighted the ions that you should memorize. Okay, so start memorizing those ions. These single atom ones are pretty easy. You can memorize them off of the periodic table because there's a pattern for these. But these you will have to memorize. There's a little bit of a pattern, but yeah, make flashcards, and that should help. And there are basic rules for ionic compounds. This first one is probably the most important. So you have to have charge, a neutral compound. So the positive has to balance the negative. Positive ion first, negative ion second. All right, so let's just see how this works with some examples. All right, sodium sulfate. So if you have the ion sheet up, that might help. So sodium, I look up the ion. It is sodium plus, okay? Sulfate, I look up the ion. First one's always positive, second one's negative. It's SO4 2 minus, okay? Now, some people like to do the crisscross thing, okay? I kind of like to say, oh, well, I need another sodium ion here. Okay, that will balance out my charges. So this formula is sodium 2, Na2SO4. Okay, so that's my sodium sulfate. All right, now iron is not going to appear on your ion sheet. That means you have to figure out the charge. But O appears. Okay, so that's oxide. So I know that oxide is O2 minus, and there's 3 of them. Okay, so I'm going to write out 3. Total charge is -6. So if I have Fe's and I have 2 of them, what does the charge have to be? Somebody can just unmute and tell me what the charge has to be for these. Plus, so this must be iron. Okay, this time we're going to write the name since we have the formula. This is iron plus 3. We write the plus 3 in parentheses in Roman numerals. Oxide. Okay, so this compound's name is iron 3 oxide. It's rust. Okay, next one, example 3. Magnesium. Again, look up the ion. Mg2 plus. Nitrite, okay, is NO2 minus. Okay, I can see that I need another NO2 minus to balance out the +2 charge to make -2. So my formula is MgNO2. And if you like to use the crisscross system, that works perfectly fine too. All right, dinitrogen monoxide. So when I see this, I say, aha, this is not ionic because I see prefixes. So this is just, oh, sorry, we're missing Ni here. This is not, I made up a new element. So this is N2O, better known as nitrous oxide or laughing gas. Okay, all right, last example. This is a hydrate. Oh, I didn't do my subscripts. Sorry, guys. These should all be lowercase, not lowercase, but subscripted. Okay, so a hydrate is an ionic compound that has water. And next week, we're going to work with the hydrate in lab. And you guys are going to dehydrate it. But the way we name these with the water, first of all, this dot right here, I know in math, it means multiply. But in chemistry, when you see this dot, it means that you have a hydrate. And it means to add 3 waters, okay, to the ionic part right here. So these 3 waters are chemically bound to these ions. So we would call this Na is sodium. This ion here, this sort of complicated ion, that's called acetate. And what we do is we use the prefixes from moleculars and we say trihydrate. Okay, so that's how we name these. So this second one is magnesium chloride. Prefix for 6 is hexahydrate. Okay, so that is, those are our naming examples, and clearly we did not get as far as I hoped. So what I'd like you to do, I'm gonna add this to the homework just because this is mostly review, and so normally this would have been part of the summer work. There is a naming and formula worksheet, so that's posted on Google Classroom. I will change the due date to next Sunday, and so complete the worksheet and then take a picture, put it on Google Classroom, or you can, download it and fill it out and upload that. So any questions before we sign off for today? Plan sheet is posted on Google Classroom, I believe, under this week. I will be having office hours today at 2:15 to 3. I meant to add that in. And I will also have office hours on Thursday night from 7 to 8. I will post that to Google Classroom to make sure.